Okay, so next we'll look at what the idea of the classes P and NP mean in terms of the actual problems we're looking at solving. We want to classify our problems the same way as which scientists classify elements. And the key technique that we're going to use is reduction. So the problem that we're going to start with, that is the key to this theory, is the Boolean satisfiability problem. And we talked about at the beginning, it's not that different than systems of linear equations, just that everything has to be Boolean variables. And so given a system of Boolean equations, find a solution. And even on its own, it's a very significant problem. It comes up and people solve huge and face huge satisfiability problems in trying to understand whether, trying to prove whether software, to verify that software works correctly. Also hardware for design and automation. People model what's going on with huge satisfiability problems and solve them. It's so basic that it even arises in physics and scientific studies in the so-called mean field diluted spin glass model. It's a very fundamental problem that is just about logical reasoning about what's going on in some complex system. Now the question is, so it's a search problem, we know that, and what that means is that if we have a solution, we can efficiently check that we have a solution. But the question is it in P? Can we find an algorithm that guarantees to find a solution in polynomial time? Now people solve huge problems, but in some sense maybe they're lucky because the instances that they're trying to solve don't cause the algorithm to run in polynomial time. But the real question is, can we guarantee that we'll get done in polynomial time? Well, what do we do? Well, for satisfiability, as I mentioned, it's pretty easy to use exhaustive search. Just try all the truth assignments. And really what that means is have an algorithm that if it doesn't find the right truth assignment, it might wind up trying all of them. But you might find one earlier, and that's what happens in practice. But the big question is, can we do anything that's really substantially more clever than SAT, than the brute force algorithm? That is an algorithm run brute force in the worst case. That's a pretty stringent definition of substantially. But that's the one that we're talking about. Can we get less than exponential worst case performance? And some people have worked on this for long enough now that most people agree that there's no polynomial time algorithm for SAT. To start classifying problems, what we're going to do is kind of adopt that as an assumption, or at least we'll classify problems according to the difficulty of SAT. And what that means is we're going to use reduction from SAT. So if we reduce SAT to some problem, as we talked about in the reduction lecture, that means if we could solve that problem efficiently, we also could solve SAT efficiently. And we're going to call a problem like that intractable. If we could solve it efficiently, we could solve SAT efficiently. We don't think we can solve SAT efficiently. That problem's intractable. So that's our meaning of the word intractable. All right, so now what are we going to do to classify problems? So the first thing is which search problems in P. So there's no really easy answers for that except for devising algorithms. But we do have this reduction technique that is going to help us. Now we can be a little more general than when we were actually designing algorithms that we're going to use. And we can have the reduction take a polynomial amount of time before we're insisting linear time. And not only that, we can take a polynomial number of calls to the one that we're reducing to. And again, all of this is about is that if you have a polynomial time algorithm for y, then the reduction gives you a polynomial time algorithm for x. And we're just trying to have the most general definition that preserves that property. And so the consequence is that if we have a polynomial time reduction from SAT to a given problem y, then we can conclude that y is, well, it's intractable by our definition. That is, it's as difficult as SAT, and we think that there's no polynomial time algorithm for it. So that's the main tool that we're going to start out with to use for classifying problems. So let's look at an example. Actually, you can work with simpler versions of SAT. You can actually reduce any SAT problem to just a form where you have a bunch of equations using literals or the negation connected with ors. So usually we use a simpler example like that. So given that SAT, given a system of Boolean equations, find a solution. So now we have another problem, ILP, given a system of linear inequalities, find a solution. So what we want to do is characterize SAT as an ILP problem. So that is, if we had an efficient solution to ILP, it would give us a solution to SAT. So let's take a look at this example. So whatever SAT problem we have, we put it in this form. And now we're going to introduce a variable C1. And for every literal in the SAT problem, we're going to put C1 greater than or equal to either the literal if it's not negated, or 1 minus the literal if it is negated. So in this case, so we have C1 greater than or equal to 1 minus x1, greater than x2, greater than x3, like that. And then we're going to have a fourth inequality that says that it has to be less than or equal to the sum of those three. So what this construction does is, if the equation is satisfied, if there's some way to satisfy this equation, then it's going to be C1 equals 1. So that is, if there's a way to make each one of these terms 1, say by setting x1 to 0, x2 to 1, and x3 to 1, then this thing will all be, those things will all be true. And then this one also will be true. And all four of these are true if and only if the equation is satisfied. And we make a little group like that for all four of the SAT equations. And then we do a similar thing with a variable that's true if and only if all of the C's are true. So this variable has got to be less than all four of these. And the only way that this thing is going to be 1 is if all the equations are satisfied. So this system has a solution if and only if there's a SAT solution. And from the solution to this system, you can find the SAT solution. So that's a reduction from SAT to integer linear programming. Because of this reduction, we feel that we're not going to have a polynomial time solution to integer linear programming. If we did, we'd have a fast solution to SAT. So that's an important piece of knowledge. We focus on this one hard problem that we know about, and that tells us another problem the reduction tells us another problem is at least as hard. And that by itself is interesting. Integer linear programming is a very important computation with lots of applications. But the amazing thing that was shown by Dick Karp in the 70s is that there are lots and lots of problems that you can reduce satisfiability to. And actually, Karp reduced SAT to the so-called independent set problem and then reduced that one to ILP. But if you do 2 reductions, it still works. If I could solve ILP quickly, I could solve independent set quickly, and then if I could use that to solve SAT quickly. So if you can prove any problem on this set, if you can reduce any problem on this set to your new problem, then that's like proving that SAT reduces to it. So if we adopt the idea that SAT is intractable, it means all of these problems are intractable. And these are lots of important problems that people were looking for solutions and couldn't find good solutions to. And what Karp showed was, including traveling salesman problem and the so-called Hamilton path problem, which is the like problem finding the that's problem of finding a path on the graph that visits all the vertices. So what Karp showed is that all of these problems are intractable. They're all at least as difficult as SAT. If we had a efficient, if we had a polynomial time solution to any one of them, would have a polynomial time solution to SAT. That was quite a powerful idea of using polynomial time reduction to classify problems in this way. In fact, it's such a powerful idea that nowadays there's maybe 6,000 papers per year with reductions from some problem that has been shown to reduce from SAT to some new problem. And these are important problems in all fields of human endeavor. So for example, the so-called protein folding problem, which in biochemistry, where people are trying to understand what's going on in living organisms, has been reduced from SAT. We'd like to solve that problem, but and that would help us understand what's going on in living organisms much better. But if we had an efficient solution for a guaranteed polynomial time solution to that problem, we'd have a guaranteed polynomial time solution to SAT, and so we don't think so. Or economics, if you just make the arbitrage problem a little more complicated and a little more realistic, where there's a little cost involved with doing things, turns out to be that you can't have an efficient solution to that one because it would imply an efficient solution to SAT. And many, many other examples, voting power in politics, experimental design in statistics, thousands and thousands of papers per year involving reductions from SAT. A very, very powerful concept that the idea of reducing from SAT. So now we have two ways to classify problems. We can find a polynomial time algorithm, and then we know problems in P, or we can develop a polynomial time reduction from SAT, and that'll prove that at least if you believe that SAT is difficult, you should believe that it'll be difficult to find a solution to your problem. So that's the first step in classifying problems.